Hello everyone, I'm Pranthar Ghosh from Dartmouth College and I'm going to talk about streaming verification for graph problems, optimal trade-offs and nonlinear sketches. This is a joint work with my advisor Amit Chakravarti and Justin Thaler. So let me begin by telling you about the model we study. In the basic streaming model, we have a cloud repository that contains the data and a client with limited memory that wants to compute a function of the data. So the client downloads the data as a stream, stores a summary of it, and then does some computation to finally give an output. But due to this memory restriction, it turns out that some problems are provably unsolvable in this model, and we often need to resort to relaxations like approximations or so. That's why we study this enhanced model called the annotated streaming model, where the client has hired a cloud service with unlimited memory to do the computation for them. So as the client downloads the stream, he outsources it to the cloud, who now ends up with the entire data, while the client, as before, has a summary of it. Then the cloud needs to perform the computation and send the answer to the client, but it might be that the cloud was hacked, or it might have incurred some network or hardware failure. That's why the client does not want to blindly trust it. And so the cloud, whom we now call a prover, sends a proof or a help message to the client, whom we call a verifier. He wants to verify the correctness of the proof and with the summary he had stored. And so he does some computation and verification, and finally outputs an answer if he thinks that the cloud was honest, or rejects the proof otherwise. This is the main idea of the model. Now let me make it a bit more formal. So a scheme is a protocol between prover and verifier, who are sometimes called Merlin and Arthur, following a long-standing tradition in complexity theory. Now they read the input stream together, and the prover stores the entire data while verifier stores only a relevant part of it. Prover sends proof or help message to verifier, who processes it with his limited space and outputs an answer if he thinks prover was honest, or rejects the proof otherwise. So a scheme should satisfy the following two properties. It should be complete, that is, an honest prover should be able to convince verifier to output the correct answer, and it should be sound, that means the verifier should be able to catch a cheating prover. Our schemes are randomized, so we want this to hold with high probability. And the terminology that I'll be using throughout the talk is that of an H, V scheme, which means a scheme that has order H bits of proof size and order V bits of space usage. So the help cost is shortened as H cost, and the space usage, that is the verification cost, is shortened as V cost. Now in designing a scheme, our goal would be to use some help to obtain space smaller than what we were already getting in the basic streaming, that is, without any help. Now in this work, we focus on graph problems. Here the input is a stream of edges of an Vertex graph, and we want to output some function of the graph. For example, we study the triangle counting problem, where we want to count the number of triangles in the graph. So the edges arrive as a stream, and we output the number of triangles. We also study the maximum matching problem, where again the edges arrive as a stream, and then we want to output the size of the maximum matching. So in basic streaming, it is known that for both of these problems, we cannot do better than storing almost the entire graph. That is, they need omega n squared space, even if we are allowed multiple passes over the input. So naturally, we study it in the annotated model, where the verifier now has to only verify the answer provided by the prover, and can ask the prover for some function of the graph as proof. So we ask if we can do better in this model. Now, what was known so far in the annotated model for triangle counting and maximum matching? Well, Chakrabarti et al. In 2009 showed that any HV scheme for the problem must have H times V at least n squared. So here we show this lower bound curve hv equal to n squared, and actually we do know 3 upper bounds on this trade-off curve. So 1 comma n squared is trivial, because if we are allowed n squared space, we can simply store the entire graph and solve the problems. Chakravarti et al. Gave an n squared comma 1 scheme in 2014, and then Thaler in 2016 balanced the h cost and v cost to give an n comma n scheme. Now, a natural question is whether we can trade off the h cost and v cost to attain more points or maybe all points on this optimal trade-off curve. In this work, we make significant progress towards answering this question. So for any integer parameters t and s whose product is n, we give an s comma nt scheme for triangle counting and an nt comma s scheme for maximum matching. Note that the product of the h cost and v cost is n squared, so this is optimal. And for triangle counting, we also give an nt squared comma s scheme, and when I'll be using the square bracket notation, I'll be hiding some log factors. So this is how it looks pictorially. Our s comma nt scheme covers all points on the upper half of the optimal trade-off curve, and our nt comma s scheme for maximum matching covers all points in the lower half of this optimal trade-off curve. Our nt squared comma s scheme for triangle counting doesn't quite achieve the optimal trade-off, but it's strictly better than what prior work had achieved. So prior work gave a t cube comma s squared scheme for triangle counting, and our results obtain strictly better bounds in terms of both h cost and v cost, and gets closer to the optimal curve. Now, let me tell you about the techniques that we use in order to obtain these results. A key technique that we exploit is the tool of nonlinear sketches. A widely used and popular tool in graph streaming literature is linear sketches, where the sketch of the graph till the jth update, let's call it gj, is updated as follows. You add some function of the jth update delta j to the sketch of g of j minus 1. Now, note that the update value doesn't depend on the sketch that was stored so far. So let's say if I give you the 100 in a graph of, let's say, 200 edges, I give you the edge updates from 100 to 200. Then without knowing what the graph was till any information for what the graph was till the 99th update, you could just sum the functions of the 100 to up to 200 edge update, and you'd know that that is the value to be added to the to G99. So note that this is not using the full power of streaming, because we are actually allowed to use the information that we have stored so far. That is the sketch of the graph Gj minus 1. So this brings me into the concept of nonlinear sketches, where the update value after for g of j minus 1 depends on both the jth update delta j and the sketch of gj minus 1. So I'll just give you an idea of how nonlinear sketches come to play in our schemes in this slide, and in a later slide I'll describe it in full details. So, as a concrete example, Thaler in ICAP 2016 used these nonlinear sketches for the triangle counting problem, where he maintained information about the triangles and edges he had seen so far. So, with the jth edge update uj vj, we get a triangle for each node w, such that both wuj and wvj were in the graph gj minus 1. So to be precise, the number of triangles added by the jth edge update is simply the wjth entry of aj minus 1 multiplied by the wvj entry of aj minus 1 summed over all w's in v. Here the aj minus 1 denotes the adjacency matrix of gj minus 1. And once you have this equation, Thaler shows that You can have a scheme where the prover does work proportional to the number of distinct values this first coordinate W can take, and verifier incurs cost proportional to the number of distinct values Uj or Vj can take, and both are n. So on a very high level, this is why he obtains protocol with H cost and V cost both n. And this is an optimal trade-off because H times V is n squared. However, it's only attained at this n comma n point, and so the trade-off is not smooth. In order to get a smooth trade-off, we use the vertex shaping technique. So suppose we want to compute summation of some function f of v, where the summation is over vertices from 1 to n. Now we use the shaping technique where we shape the vertex index vector into a two-dimensional array. This is a technique that Amit and myself used in a paper in random last year. So because of this shaping, the vertices are renamed as these pairs x comma y, such as here the vertex 1 is named as 1 comma 1, 2 as 1 comma 2, and so on. So therefore, the function can now be defined over pairs x and y, x, y, such that the function is basically represented as this 2D array. So given any t and s, whose product is n, we can shape it into a t cross s array, and therefore the answer, which was previously a summation of f of v with v running from 1 to n, becomes a double summation of f of xy with one summation running from x from 1 to t, and the other is y running from 1 to s. And then we can again obtain a scheme where the h cost would be proportional to the distinct values of the first coordinate, that is t, and the v cost would be the number of distinct values this second coordinate y can take, and that is s. So instead of a cost of n, we can split it into h cost t and v cost s for any t and s whose product is n. And this is how, on a very high level, we obtain a smooth trade-off. So to sum up, Taylor in 2016 used nonlinear sketches to obtain a trade-off that is optimal but not smooth. And Amit and myself, we used this vertex shaping technique to obtain a smooth trade-off, but it was suboptimal. So here in this work, we kind of team up and we succeed in combining our techniques to obtain a scheme with both optimal and smooth trade-offs. Now I'll describe our triangle counting protocol for space larger than n in details. So recall that the quantity within this outer summation was the number of triangles added by the jth edge UJ-VJ. So if we sum it over all UJ-VJ in the string, we get the total number of triangles. Then for some parameters t and s whose product is n, we shape the n cross n adjacency matrix capital A into a t cross s cross n array small a. So if W becomes a tuple x comma y, then the W vth entry of capital A becomes the x comma y comma vth entry of small a. So we rewrite the equation in terms of small a like this, and then we take this summation over x outside. So this is the rearranging the summation, and then if we fix an x in 1 to t, the quantity within this outer summation becomes a function of x, which we now make a polynomial function of x. So how do we do that? Well, using Lagrange interpolation, we can get polynomial a tilde that agrees with a at all values in its domain, and a tilde is defined over some large finite field capital F. Then we can simply replace a by a tilde, and now this quantity within the outer summation becomes a polynomial function of x. So the polynomial p of x is defined in this way, and then this quantity is captured as p of small x. So the quantity we are looking for t can be expressed as a sum of px, where x runs from 1 to t. And note that the degree of this polynomial p is 2 times t minus 1, that is order T, and hence the number of monomials or coefficients required to express P is also order T. So these were the takeaway from the last slide, that the P of X was defined in this way, such that the answer T is summation of Px with X running from 1 to T, and degree of P and number of monomials in P are both ordered T. So now we are ready to describe the protocol. Verifier picks an element R in F uniformly at random and maintains with stream updates A tilde J of RYV for all Y in 1 to S and all V in 1 to N. Note that these values, by substituting it in this equation, he would be able to compute P of R and maintain that value P of R. So now verifier prover sends the verifier polynomial P hat, which he claims to be identical to P. Verifier computes P hat at the point R and compares it with the value P of R that he had computed. So if they are equal, then he believes that P and P hat are the same, and so his output summation of P hat X as the answer according to this equation. And if not, he is sure that the prover is cheating him, and so he rejects the proof. Now for correctness, note that completeness is immediate, since if the prover is honest, then simply by the math we always output the correct answer. But for soundness, we may incur an error when P was actually not equal to P hat, but this check had passed. So we know that if P is not equal to P hat, then P of R will not be equal to P hat of R with probability at least 1 minus degree of P over mod F. This is the univariate version of Schwarzschild lemma. That is because P, the polynomial P minus P hat, can only have at most degree of P many twos. So recall that the degree of P was order T, which is at most order N. So if we take the field size to be some large enough polynomial in N, then the soundness error would be at most some small number, that is 1 over poly N. So now let's analyze the costs. So recall that the number of monomials required to express P is order T. So the H cost would be O tilde T, where each coefficient is in this field, so will be of size log n. So this O tilde notation has log factors, and the H cost is O tilde T. And the verifier stores a field element for each Y in 1 to S and each V in 1 to N. So the V cost he incurs is O tilde of N times S. Therefore, we get this result that for triangle counting, for any T and S whose product is N, we get a T comma NS scheme, and thus we obtain all points in the upper half of this optimal trade-off curve. Now I'll give a very brief overview of the proof for the case where space is smaller than N. So recall that in the last protocol, we shaped this first vertex W into 2 parts, but now we would shape uj into uj1 uj2 and vj into vj1 vj2. And with this idea and a lot more work, we show that we can express T as a sum of values of a multivariate polynomial P, which has ordered nt squared monomials. So this time it's a multivariate polynomial, and that can be evaluated at a single random point using order S space. So as before, we would just use this value to do the sum check and check that the polynomial provided by the prover is correct. So because the prover sends this polynomial, we would incur an H cost of nt squared O tilde nt squared, and our V cost would be O tilde S. So we get an nt squared comma S scheme that improves over the earlier result and gets closer to the optimal trade-off curve. Now let's switch gears to talk about the maximum matching problem. Here, given a graph G, we want to compute the maximum matching size of G, and the prover shows it in 2 parts. So say the maximum matching size is K, then he first shows that it's at least K, and then he shows that it's at most K. So showing that it's at least K is actually easy. you can simply send a matching that has size k. So the maximum matching size would only be larger. And it is known how to verify that it is indeed a matching in the graph. But this proving that it's at most k is actually challenging. And for this, we use the Tut-Burge formula, which says that the maximum matching size is half of minimum of mod u plus mod v minus odd of g minus u, and the mean is taken over all the vertex subsets u. And odd of g minus u is basically the number of odd connected components of the induced subgraph g minus u. So this is the formula. And then the prover can just show vertex u subset u star, where k is equal to half of this mod u star plus mod v minus odd of g minus u star. Then we know that since this is the minimum over all vertex subsets u, the maximum matching size would be at most this value k. And so we see that the complicated quantity that needs to be calculated here is odd of g minus u star, and that has to deal with connected components of this subgraph, and that's why it boils this maximum matching problem down to a connected components problem, which is as follows. So we would get this problem where we are given a graph G, a subgraph H, and components vertex subsets C1 to CL of H, and we want to check if they are pairwise disconnected. Now observe that if they are pairwise disconnected, if and only if there is no such crossing edge there between some Ci and Cj. So in other words, we have to check if the total number of edges in H is equal to the sum of the number of edges in the Ci's. So for this, then we define this problem of induced edge count, where given a string of edges followed by a string of subsets E1 to UL, we want to count the sum of the number of edges in the UIs. We succeed in getting an HV scheme for this problem for any HV equal to n squared, and for this we use these techniques of vertex shaping, nonlinear sketches, and polynomial sum check. Now once we have this scheme, we can use it as a subroutine for this connected components problem. We invoke it with the single subset H to compute the number of edges in H, and then we invoke it with separately with the CIs and to compute the total number of edges in the CIs, and simply we check that if they're equal, and this solves the problem. So basically for the cost analysis, the induced edge count protocol had cost HV equal to n squared for any HV with HV equal to n squared, and for note that to show the lower bound on the matching size, we needed to send an actual matching which can have size theta n, and so our H cost would be at least n. So basically we get an nt comma s scheme for any n t times s equals to n, and cover all these points in the lower half of the optimal trade-off curve. We also have a number of other results that I could not go over in detail in this talk, but I'd be happy to talk in the live session. We show applications of our induced edge count subroutine to a variety of graph problems. Like for triangle counting in the edge arrival model, we get better schemes for sparse graphs. And for the vertex arrival model, we get an HV scheme for any HV equal to n squared. We also show that it can be used to solve fundamental graph problems like maximal independent set, acyclicity testing, directed graphs, and topological sorting. And we get optimal smooth schemes for all these problems, which are hard in basic streaming. We have a number of results on shortest path problems, like we get better schemes for the unweighted ST shortest path problem, and interesting schemes for both unweighted and weighted version of the single source shortest path problem. Now I'd like to wrap up with some open problems. The obvious ones arising after this work are whether you can settle the complexity of triangle counting and maximum matching in the regimes of h cost greater than n and h cost less than n respectively. We ask if we can remove dependence on path length for ST shortest path and diameter for single source shortest path, which would then make the schemes for these problems optimal. And finally, we ask if we can show better lower bounds than HV greater than equal to n squared for any explicit graph problem. Note that a related open problem is a major open problem in communication complexity, which asks whether we can break the square root n barrier in the Marlin-Arthur communication model. With that, I'd like to end. Thank you for listening.